So far, this large unit on work and energy has been divided into two parts. In the first half of this unit, we went through the details of the work-energy theorem, and in doing so, we looked at the work done by all types of forces, not just conservative forces such as gravity and the spring force, but, for example, pushing forces and the forces of friction. However, in the second half of this unit thus far, we've only been concentrating on the conservative forces of gravity and the spring force, leading to expressions involving energy conservation. How do you incorporate into a description of energy conservation the other types of forces we've looked at, such as a manual pushing or pulling type of force and the force of kinetic friction? Well, those types of forces are referred to as non-conservative forces. The easiest way to understand exactly what is meant by a non-conservative force is to move directly to an example. Let me go ahead and read that example to you here. Okay, a chair with a mass of 5 kilograms is horizontally pushed by a constant force of 20 newtons over a closed path with a total distance of 12 meters. Okay, the shape of the path itself is completely unimportant. However, what is important is that the path is closed. What that then means is that you start and stop in the same position. I like to visualize the 12-meter distance that is given here in this problem as a 3, 4, 5 meter right triangle. I'll draw that as a top view of the situation in just a few moments. Okay, and then the surface has a coefficient of kinetic friction equal to 0.3. Calculate the work done over the closed path by the manual pushing force and by the force of kinetic friction. In doing so, we'll get an understanding as to what is meant by a non-conservative force. Okay, let me draw a top view of the scenario. Right here is our chair, we'll say of mass M equal to 5 kilograms. And then I basically just push it like this. Let's say I push it in this direction 3 meters, in this direction 4 meters, and back to where I started like so, in this direction here, or this distance of 5 meters. But the total distance over which I push the chair is just a total of 12 meters. We'll think of that as the magnitude of our overall displacement vector. Okay, once again for simplicity, let's say that as I push this chair, I always keep the force diagram the same. In other words, let's just say I push the chair in this direction, push it in this direction, and then push it in this direction like so. So then therefore the relationship geometrically between the pushing force, the force of kinetic friction, and the displacement vector will always be the same. So I'm dramatically simplifying the situation just for ease of calculation. But once again, what's important is that we're pushing this object over a closed path. Okay, so now as I push the object, here as seen from the side is our force diagram. We have first of all the normal force and the force of gravity. Right here is the F push to the right hand side. Opposing the motion is the force of kinetic friction. And I'm always pushing in the direction that we're moving once again to keep the geometry simple. Okay, now numerically we're given that the F push is 20 newtons. And then we're also given the coefficient of kinetic friction between the chair and the surface below is 0.3. Once again, let's emphasize that what we're doing is we're calculating the work done by the manual pushing force and the force of kinetic friction over a closed path. So calculating work over a closed path. Okay, now let's take a look at the work done by the pushing force. So then therefore the work done by F push, this is like going back to the good old days, if you will, of early in this unit, where we're just practicing calculating the work done by various forces. So this is going to be the dot product between F push and delta R. They both point in the same direction, 0-degree angle between them. Cosine of 0 degrees is equal to +1. So this basically just ends up being force times distance. Okay, now numerically, let's go ahead and calculate this value. So F push was given to us as 20 newtons and then multiplied by the displacement of 12 meters, and this is 240 joules. Okay, of course this is easy enough to calculate, but notice what it's not equal to. It's not equal to 0. So then therefore a manual pushing force is a non-conservative force, and in this case this non-conservative force adds energy to the chair. So in other words, the chair's total energy is not a conserved quantity. By pushing on it, you're adding energy to it. That's what this statement here says. So this non-conservative force adds energy to the object. The object's energy is not a conserved quantity. We're adding energy to it by pushing on it. Okay, given that, you could probably guess what's going to happen now with kinetic friction. So let's go ahead and calculate the work done by kinetic friction over this closed path. Okay, so the work done by kinetic friction is the dot product between the kinetic frictional force vector and the displacement vector. Once again, it's like going back to the beginning of this unit when practicing calculating work. So we have then the magnitude of the first vector times the magnitude of the second vector multiplied by the cosine of 180 degrees. There's a 180 degree angle between f sub k and delta r. So we pick up our negative sign, like so. And the force of kinetic friction is the coefficient multiplied by the normal force. For this simple horizontal situation, the normal force is equal to the chair's weight. So then therefore, the work done by kinetic friction is the following expression, which we have seen before for various other situations involving horizontal displacements. Okay, let's go ahead and calculate this number. So negative 0.3 times the mass of 5 times 9.8 times a total of 12 meters. This comes out to be negative 176.4 joules. Okay, once again, an easy enough number to calculate, but notice what it's not equal to. It's not equal to 0. So then therefore, this non-conservative force removes energy from the object. Obviously, it's removing energy as heat. So this non-conservative force removes energy from the object. So now let's combine together everything that we have seen in the unit thus far. Let's incorporate it all into the work energy theorem. What we have seen is that there are two types of forces. There are conservative forces that have potential energy associated with them, and non-conservative forces that either add energy to an object or remove energy from an object. How do you combine all of this together into a single expression? This is the expression I actually have been working towards steadily over the course of this large unit on work and energy. From this point forwards, when it comes to homework problems and eventually exam problems, you could just use this equation directly, and that's perfectly fine. So here's then how we arrive at that expression. As is always the case, we always start with the work energy theorem. Net work equals change in kinetic energy. But now we recognize that the left-hand side of the expression is two things. It's the work done by any non-conservative forces that may be present, such as a pushing force or the force of kinetic friction. Plus then the work done by any conservative forces that may be present, such as gravity and the spring force. Okay, now the work done by conservative forces, remember, is the opposite of the work against conservative forces, which is then therefore the changes in potential energy. Whether they be changes in gravitational potential energy, or changes in spring potential energy. And now I'll go ahead and take these two potential energy terms and move them to the right-hand side of the expression. When I do, I come up with the one equation that I've been working towards over the course of this entire unit. That is then therefore the following. Work done by any non-conservative forces results then in changes in kinetic plus changes in the various forms of potential energy. Like so. This is the one expression that we will use going forwards from this point forwards for the remainder of the unit. Once again, this is your starting point regarding anything involving energy transfer over the course of this unit. Okay, now the left-hand side of the expression. The left-hand side of the expression is still interpreted as the change in the total energy E of the object. So then therefore, if no non-conservative forces are present, there's no pushing force and there's no kinetic friction, then this right here is equal to 0 and the energy is conserved, like we've seen in previous examples. However, if you have a pushing force present, then this would be a positive number. This then means that the final energy of the object is greater than the initial energy. In other words, by pushing it on an object, you add energy to it. If this number here, however, is negative, as it would be in the case of the work done by kinetic friction, this then means that the final energy of the object is less than the initial energy because kinetic friction is removing energy as heat. In the second portion of this lecture, I'll do two examples that involve the use of this expression. Most of the time, when it comes to basic problems involving the use of this expression, the work done by the non-conservative force is usually going to be the work done by kinetic friction. So we'll take a look at that in the context of the two examples that will follow in the next video.